Yeah.
My initial idea was to use monocolic research. The issue game process can be abstract as the process of making decisions in the game tree. So using monocolic research to implement a game agent is suitable. Each node of the game tree corresponds state. Each edge of the game tree corresponds a decision made by a player or agent. The process of playing a game is like making decisions in the game tree. So the goal is to maximize the rewards of the player and minimize the rewards of the opponent. Please help me play the demo. According to the demo, although MCTS can solve some problems with large exploration space effectively, even based on the MCTS performance is not good. And this is because the MCTS used in the game is online training, which means that MCTS didn't do enough iterations in the limited time. So it didn't converge to a good solution. That's all my part. Please welcome the next member.
Okay. My job is to implement reinforcement learning. And we try to use Q-learning to model this agent because Q-learning is optimal. But for us, for this game, Q-table is so hard to create because the state space as well as the action space is too large. And it's so hard to create the Q-table. So we use another way. The first one is approximate Q-learning. Approximate Q-learning is to get the features from a state, and the first feature we get is the number of rings, and the second feature is the number of counters, because the main goal is to remove 3 rings and after 5 sequence. The second method we use is deep Q network. We use deep Q network to evaluate the Q value and to make decision with the Q value, and update the Q value by the next state we choose and in another in the target network. And you can say this we map the state as well as action into vectors and use a network with one hidden layer. And now we show you the implementation. And the performance of this DQN depends on the training of its. So let's welcome the next one.
We improved BFS, which can beat the original BFS. Let's see the demo. The challenge is how to evaluate each action. We use the inspiration from the MCT to calculate the discount reward by multiply 0.9 for one step, so that the reward for each action is not only determined by the original reward the agent can get from the state, but also how much steps the agent need to get this state. On the other hand, we take the opponent's reward for each action and their future rewards into consideration. We will minus the rewards the opponents can get from our calculated reward. However, BFS is a blind search. The challenge is that it wastes too much time to find the reward. We have tried to create heuristic functions for it, and it will also have some improvement. In the future, it can be improved by training offline or cut branches.